Hey everyone, and welcome back. We are into the final two lessons of our Unit 3. So this one is going to be about the rational solutions of polynomials, and the next one's going to be about the irrational ones. So these are kind of going to go hand in hand. Now it does follow very nicely from where we left off in our last lesson. So we did the long division and synthetic division of polynomials. We're going to use that today to try and find out, okay, what are some of the zeros of a polynomial, which will also tell us what the factors are too. So we're going to look for factors and zeros today. And we're going to stick with just rational solutions today. So that means that every solution you find could be put on a number line. And then we'll also talk about complex solutions in our next lesson. So last video, we divided polynomials. We did it with factoring, long division, and then synthetic division. So just one thing to take a look at. When we are given a polynomial, it's going to come in a certain degree. So say like this one in red is x, like cubed would be the highest degree of x. So this isn't the graph of x cubed, but this one would be a degree of 3. The number of solutions is 3 real solutions. Now, if you think about the second one over here, also an x cubed would be the highest degree, but there's only one real solution, and then there are 2 complex, so I don't know where those complex solutions are. But if the degree of a polynomial is odd, so 1, 3, 5, 7, 9, and so on, you're always going to have at least one real solution. You can see it on the last one over here as well, because it's going to go negative infinity, positive infinity. So regardless of where the turning points are, it's going to cross the axis at least once, if not more. Even ones, on the other hand, so this one was an x to the power of, I think this is an x to the power of 6. So actually, this should be a 6. We've got no real factors. It doesn't ever actually touch the axis, and it's kind of hard to see it here, but there are actually like a bunch of mini turning points in this, and then you've got your one down here as well. So we would say, all right, there are no real factors, they're all complex, which is possible if the degree of the function is even. And then the last one, this would be an x to the power of 5. So we've got 1, 2, 3, 4, 5 zeros, all real. And I'm just saying I know they're all real because I made this so this was an x to the power of 5. If it had been like an x to the power of 7, we might say, oh, there's 2 complex solutions in here somewhere as well. We just can't see where they are. So long story short, we are going to be testing for real solutions today. So we're going to be looking at ones that look like the first one and the last one, where all the solutions are ones that actually hit the number line. So they're real solutions. In our next class, we'll deal with ones like option 2 and 3, where you're going to have complex roots, more so like option 2, where there will be at least one real, and then maybe 2 or more complex solutions. All right, so first thing, we want to just think back to our long division and synthetic division and just ask ourselves, if we were given the scenario, x minus 4 was the divisor, and we want to know, was it a factor of the polynomial? If we checked using long division, so let's have a look. Let's do long division on this one. So we got x minus 4 going into, let me do that one again. So x minus 4 going into x cubed plus 6x squared minus 19x minus 84. So x goes into x cubed, x squared times, so we would get x cubed minus 4x, I'm sorry, that should be an x squared, not x cubed. 4x squared times, draw your line, subtract, so this is going to change sign, and so is that one. So 4 plus 6 is 10x squared. So then you would have x times what is 10x squared, it would be plus 10x. And that would be minus 40x. So the 19 has come down. Become minus 10x squared plus 40x. So that would be 21x. And then the 84 is coming down too. X times what is 21? It is 21. So we would say, all right, 21 times minus 4 is minus 84. So we get 21x minus 84. Change the sign. Everything cancels, so we have a remainder of 0. If you get a remainder of 0, that means that the divisor, x minus 4, divided evenly into the dividend and gave you a quotient with no remainder. So we would say, therefore, so remember a little triangle with dots, therefore, x minus 4 is a factor of the polynomial x cubed plus 6x squared minus 19x minus 84. Side note, we can also use the quotient to find remaining factors if they exist. Let's just do the same thing again, but this time using synthetic division just to show that it would give us the same solution. So if x minus 4 is the divisor, we are going to use positive 4 as our synthetic divisor. So 4 is going up there. We've got 1, 6, negative 19, negative 84. Draw our line. 1 comes straight down. 1 times 4 is 4. So we get 10. 10 times 4 is 40. 40 minus 19 is 21. 21 times 4, 84, plus negative 84 is 0. So again, remainder of 0, and we would say, yes, it is a factor. So both ways are going to work, but the key is that if you get a remainder of 0, then that number is a 0 of the function, and it's also a factor. So if you're talking about the factored form, it would be a factor of the value. So your turn. Just determine if x minus 3 and x plus 4 are in fact factors of the given polynomial. It's the same polynomial for both of them, but you're testing to see if one, both, or neither of those factors are in fact factors of the polynomial. Try it out. You can use long division or synthetic division, then come back and see how you did. Okay, I'm just going to do synthetic division for both because it's just that little bit faster and more tidy. So we got 1 minus 3 minus 22 and 24. I'm going to really squeeze it in here. So 1 comes straight down. 1 times 3 is 3. 3 minus 3 is 0. 0 times 3 is 0. So we got minus 22. Minus 22 times 3 is negative 66. So that would be a minus 42, which regardless is a no. X plus 4. So the divisor would be minus 4. And 1 minus 3 minus 22, 24. 1 comes straight down. 1 times minus 4 is minus 4. So that's minus 7. Minus 7 times minus 4 is 28. 28 minus 22 is 6. 6 times minus 4 is negative 24. Cancels down to be 0. So we would say yes. X plus 4 is a factor, which means minus 4 is one of the zeros of the quadratic, or of the cubic. Okay, so now we're going to actually be presented with polynomials where you're not given any like, oh, test this factor, is this a 0? Now you have to actually figure out what are the factors and what are the zeros. So rational root theorem is a theorem that we're going to use here. And this basically tells us that if we have a polynomial, so I'm just going to give you like an example one, say 2x cubed plus 4x squared minus 7x plus 10. The roots, so the possible zeros, are always going to fit the form m over n, where m is going to be a factor of the constant and n is going to be a factor of the lead coefficient. So if you think of that, the factors of 10 are 1, 2, 5, and 10, and also minus 1, minus 2, minus 5, and minus 10. So you can make pairings out of those numbers to get 10. Factors of 2 are 1, 2, -1, and -2. So then you have to make combos of those being divided. So 1 divided by 1 is 1. So we would say possible zeros. So we've got +1. We've also got -1. So 1 divided by -1 or -1 divided by 1, positive or -1. Okay. 1 divided by 2. So that's the 1 up here divided by the 2. So we've got plus or minus a half. We've got 2 over 1. So that would be plus or minus 2. 2 over -2 is still just -1, which we've already accounted for. 5 over 1. We have plus or minus 5, but we could also do 5 over 2, so plus or minus 5 over 2. And then we've got plus or minus 10, and then 10 over 2 is just 5, which we've already accounted for. So that's all of our possible zeros. So we've got 2 for each one. So 2, 4, 6, 8, 10, 12 possible zeros. So there's 12 numbers that could be zeros of the function. It is a cubic, which means that there is a max of 3. Real zeros. So max of 3 zeros, we know a minimum of one of these must be real, because we saw a cubic that it's going to have that like N shape, so it's going to have to hit the axis at least once. So if 3 of them are zeros, and we said there's 2, 4, 6, 8, 10, 12 possible zeros, 3 out of 12, you have a 1 in 4 chance of guessing the correct one. Or another way of thinking is we probably have to test at least 4 of them before we actually find one. That's just your statistical chance of guessing or figuring out one of your zeros. Some strategies I would use though, I would start close to 0 and work your way out. So like the plus minus 1, the plus minus a half, the plus minus 2, and then the 5 over 2. Like I would start with those and then make your way out to like the 5s and the 10s. Typically you're going to have one zero that's close to 0, and then the further away you get, I think the lower your odds get sometimes. So we're going to have to test a bunch of different zeros to try and find one that is actually 0 or more. I mean, we can try and find all of them. So in our case, the constant is -15, the lead coefficient is 1. So this one's a little bit easier when the lead coefficient is not anything greater than 1 or between 0 and 1. So if it's 1, it makes life a little bit easier because then we only have to test the factors of -15. So we would say -15. Factors are 1, 3, so 1 times -15, 3 times -5, we have 5 times -3, and 15 times -1. So that's 8 different numbers there. So possible zeros are going to be, I like to put them in numerical order. So we got plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. Now I will say that there are other ways to factor this. I'm merely showing you this way. Like if I was looking at this, it's 4 terms. I might look and see like, could I factor by grouping? Is there anything common I could take out? It doesn't look like it at first glance, so this is probably going to be the best way to do it anyway, but just in case, that's what I was thinking. So how we set this up, we do a table. So we're going to do synthetic division, we're going to do it in a table format, so we're not going to take up as much space as we have done in the past. So your possible zeros, your m over n values, are going to go down the left column. You're going to have to separate the plus and the minus now. So I go close to 0 typically, so I'll do something like -1 and +1, -3 and +3. And if I need to go further, I'll go down through those. It's a cubic, so I'm expecting 1 to 3 real zeros out of 8 possible zeros. So if I test, so what's that? 3 out of 8. So about every 3 ones I test, I should find one. So my goal will be, by the time I get to -3, that I will have discovered at least one of the zeros. if I have to go into the next one, I'm pretty confident that I'm going to find one very quickly at that point. Across the top, this is what your synthetic division setup is going to be, like exactly as you did before. So coefficients and constants. So the coefficient of x cubed is 1. Coefficient of x squared is 3. And we've got minus 13, and then we got minus 15. You're going to treat the numbers over here, the possible zeros, as your synthetic divisors. So think about how that worked. We had the 1 would drop down and would always be in the quotient. So if I'm going to do this separately just so you guys can visualize what I'm talking about. So we're doing a synthetic divisor of minus 1. We've got the 1, the 3, the minus 13, the minus 15. Drawing our line, and the 1 just dropped down. So the 1 here and the 1 here are the exact same thing. 1 times minus 1, so I'm going to do this. 1 times minus 1 is negative 1. Now you do have to hold that number in your head for a second. So you're going to say, okay, minus 1 plus 3. So now we move over a column. Minus 1 plus 3 is 2. So essentially on our synthetic division, normally we would do 1 times minus 1 is minus 1, and then we would bring down that 2. We're basically cutting out this middle row. We're saying we're going to hold whatever that number is in our head. So when I do 2 times minus 1, it's negative 2. I'm going to hold that number in my head and then add it to the negative 13. So that's going to be negative 15. And then negative 15 times negative 1 is positive 15. And positive 15 minus 15 is 0. So in fact, we found one of our zeros on the very first try, which can happen. It's why it's nice to start near 0, because you increase your odds, I think, of finding a 0 a lot of the times. So remainder is 0. Therefore, minus 1 is one of my solutions that I'm looking for. It is one of the zeros. We can continue to test. So you could test every one of the possible zeros until you find the 3 that actually do work, or you only find 1, and that means that there's going to be 2 complex roots. The other thing we can now do, though, we know that if x equals negative 1 is an answer, that means x plus 1 is a factor, and the other factor then is the quotient, which is x squared plus 2x minus 15, and that's coming from our quotient value, or that the numbers that were remaining. So our remainder is technically out here. So it's the 1, the 2, and the negative 15. And you just look to see, can that be factored? So factors of negative 15 that out to be 2, that would be x and x, positive 5 and negative 3. So pretty much once you find that first factor, if you're left with a quadratic, you can take a look and see, hey, can I factor it? If not, maybe put it in quadratic formula. You can continue with synthetic division if you would like, but that may be the slower option. So if I were to go continue testing zeros, I wouldn't, so minus 5 is one of them. So I'm looking down here and I'm saying, okay, this is minus 1, minus 5, and positive 3. So if I tested positive 1 and negative 3, I wouldn't have gotten a 0. It would have been the 3 and the negative 5. I would have had to like get all the way down there before I would have found my other 2. So you can do it that way. You can do it with factoring the remaining quadratic. I'm going to show you another one in a second where it's going to be like another round of the synthetic division because it's going to be so big. So yeah, it changes each time you do it, but it's basically a repetitive over and over again. Just to show you though, what would have happened if I put 1 in. So this one, the first column 1, comes down, it would be the same for all of them. So that would be 1 across the board. 1 times 1 is 1, plus 3 is 4. 4 times 1 is 4, minus 13 is negative 9. Negative 9 times 1 is negative 9, minus 15 is negative 24. So not a 0. So same thing with minus 3. Okay, let's step it up a little bit. So we're going for a polynomial that has a degree of 4, which means that we're expecting at least 4 solutions. So, sorry, not at least, exactly 4 solutions. Now, they could be 4 real, they could be 2 real, 2 imaginary. We don't really know what we're going to get yet. But we're going to go through the exact same process. So we're looking at the constant value 24 and the Lie coefficient, which again is 1. Nice to have just 1 again. So factors of 24, and I usually just do this off in the corner somewhere. So we got 1 times 24, so you can actually write those down, 2 times 12, 3 times 8, 4 times 6, and then we've got the negative version of all of those as well, because you could do 2 negatives and you would get 24. So my potential zeros, there's actually quite a lot of them this time. We've got plus or minus 1, plus or minus 2, plus or minus 3, plus minus 4, plus minus 6, plus minus 8, plus minus 12, and plus minus 24. So we've got, let's see, 8 times 2, 16 zeros. We're looking for 4, so we've got 4 out of 16 possibilities. So we have a 1 in 4 chance. So we're probably going to test about 4 to 5 of these before we're going to find a 0. Now we may get lucky and get it in the first one, we may get it in the second, but just your probability of guessing a correct 0 is about 1 in every 4 guesses. So we set it up, our table again, the m over n, which in this case is just factors of 24. So that's going to be our column. Across the top, we've got 1, minus 4, minus 7, 22, and 24. No zeros in there because every degree of x was accounted for. And then my zeros I'm going to test. I like starting close to 0, so I'm going to do minus 1 and 1, minus 2 and positive 2, minus 3 and positive 3. If I don't find one by then, I'll consider myself unlucky. And then, I'll keep going, but I'm going to try that for now. I want to find 1 first of all. All right, so as always, the first number is going to come straight down. So 1 is going to be the same for all of these. We've got 1 times negative 1, so times the synthetic divisor. So 1 times negative 1 is minus 1, minus another 4 is minus 5. Minus 5 times minus 1 is positive 5. Minus 7 plus 5 is minus 2. Minus 2 times minus 1 is positive 2. So 22 plus 2 is 24. And 24 times minus 1 is minus 24. So hey, look at that. We've got another one on the first try. Doesn't typically happen that way, but love it when it does. Okay, so we've got a 0 at minus 1. Perfect. Let's see. So typically what I would do at this stage is as soon as I found 1, so I know minus 1 is one of my zeros, I actually stop testing because again, there's 16 zeros to test. It's a lot. And you're still not guaranteed that all of them are going to be real. So you could go through all 16 of those and find out that 2 of them are real and 2 are imaginary. So it doesn't often work out well for you to go and do the whole thing. But what we do know now is that in factored form, if minus 1 is a solution, that means x plus 1 is a factor. And the quotient is also given to us now. So we've got x cubed minus 5x squared minus 2x plus 24. Now what you can do is you can say, all right, I know one factor, let's keep going. So now I'm going to factor the cubic instead. So you pretty much start the process over again. So I'm just going to erase what I don't need from that first synthetic division. And now we look at, again, factors of 24. So my possible zeros actually haven't changed, which is great. So I'm going to go m over n. And we've got 1 minus 5 minus 2 and 24 this time. So my polynomial's gotten 1 degree smaller. It's unlikely that -1 is going to be another 0 unless there was a multiplicity of 2. So we can test it again, or we can leave it out. I guess we may as well test it again just in case. So I'm going to put my positive negatives in there again. So now this time there are 16 potential zeros. We're looking for 3 of them. So our odds of guessing a correct one have actually gone down a little bit. So now you're talking about 1 in 5, 1 in 6 being an actual 0. So I'm going to test 4 just to see how I do, hoping that it's going to be one of these, and if not, I'll have to keep going. So 1 is going to come straight down in each case. 1 times -1 is -1, so that's going to be -6. -6 times -1 is +6. +6 minus 2 is 4. And then 4 times -1 is -4, so we have a remainder of 20. So -1, not a 0 for a second time. Let's go +1. 1 times 1 is 1. -5 is -4. -4 times 1 is 4. 4 minus 2 is 2. 2 times 2, or 2 times 1 is 2, plus 24 is 26. So no go again on the first two. I'm going to switch color here so we don't get too confused. So I'm going for the -2 now. 1 times -2 is -2. -7 minus 2 is -5 minus 2 is -7. -7 times -2 is 14. 14 minus 2 is 12. And 12 times -2 is -24, plus 24 is 0. Sweet, so we found another 0. So now, again, going into that factored form, we know from above that x plus 1 is a factor of the original. We now know x plus 2 is another one. And then still remaining is an x squared minus 7x plus 12. And at the quadratic stage, you could do synthetic division again. So it's actually another way to factor quadratics, which we didn't look at before when we were doing quadratics. You could do factors of 12 and then test them to see which one actually gives you a remainder of 0. But we also know we're able to just factor quadratics. What are the factors of 12 that add up to be -7? So factors of 12 that add up to be -7, that would be -4 and -3. So we could say this is x minus 4, x minus 3, and then we've still got our original factors. So this is our final answer. If we're asked for the zeros, so if we're asked for the factor form, this is what it is. If we're asked for the zeros, we've got -1, -2, 3, and 4. So those would be my 4 zeros. So it's going to cross the axis at those 4 points. So this is one where you're going to do the synthetic division twice. So it turns out if we had stayed on the original function and kept testing zeros, so done all 16, we would have found the 4 eventually. You would have had to have gone 7 or 8 rounds deep before you would have found them all, but it didn't have to go the whole way through, so it wouldn't have been too bad. But doing the multiple rounds of synthetic division, so like taking that first quotient and then doing synthetic division of that one, does kind of speed up the process a little bit. So I mean, we only ended up testing 4 zeros altogether to find all 4. So that's a great return in terms of our time. But you can choose to do it whichever way you want to try. All right, your turn. Find the zeros of the following. So testing them out using synthetic division as opposed to doing anything like factoring by grouping or anything like that. So I want you to practice that synthetic division. Pause the video, come back, let's see how you did. All right, so we've got -20 and 1 is my lead coefficient, so don't have to do anything special there, just factors of -20. So that'll be 1 and -20, 2, -10, 4, -5, 5, -4, and so on. So 1, 2, 4, 5, 1, 2, 4, 5, 10, 20. I need the positive and negative versions of both of those. So we got plus or minus 1, plus or minus 2, plus or minus 4, plus minus 5, plus minus 10, and plus minus 20. So 1, 2, 3, 4, 5, 6. So I've got 12 possible zeros. It's x to the power of 3, so it's a degree of 3. So I'm looking for 3 zeros. So again, I have about a 1 in 4 chance of guessing correctly. So let's make our table. We've got 1, 2, negative 19, negative 20, m over n. On the left column, I'm just putting in possible zeros. I'm going to start close to 0 itself, so minus 1 and positive 1, minus 2, positive 2. I should be able to find a 0 within the first 4, just based on probability, but just in case, I would then next go into the 4s to try and find one. All right, so the first column, the number is always going to be the same. It just comes straight down. So 1's down the board. 1 times minus 1 is negative 1. 2 minus 1 is positive 1. So you're just carrying that negative 1 in your head. 1 times negative 1 is negative 1. Minus 19 times minus 1 is minus 20. And minus 20 times minus 1 is positive 20. Minus another 20 is 0. So it's actually turning out very fortunate in this case. I did not plan it this way, that my zeros were going to be the first thing I tried every single time. Once more, you could keep going down through the list, but what I like to do is take that quotient now, so the x squared, 1x minus 20, and see, can I factor that? So can I get my 2 zeros in one go? So factors of negative 20 that add up to be 1, well, that would be 5 and negative 4. So I'd have x plus 5, x minus 4, and then the factor I found already was x plus 1. So that's from figuring out that minus 1 is in fact a 0. So that's the factored form, and then zeros, x equals, I guess I'll try and do this in order, minus 5, x equals negative 1, and x equals positive 4. So if I were to go down through the synthetic division, I would have found 1 on the first try, and then it would have taken me to positive 4, and then negative 5 to find the next one. So I would have had to go 1, 2, 3, 4, 5, 6, 7 rounds deep before I would have found all 3 zeros. Versus just doing 1 round and then factoring the quotient, I think I found my answer very quickly in comparison. So thinking about different strategies you can try there. All right, let's try this one. We have x to the power of 4 minus 2x cubed minus 3x squared plus 4x plus 4. So this is one of those bigger ones because you're going up a degree for x. Lead coefficient is still 1, and 4 is my n number. So this is actually going to be very few factors. So we're going to have 1 times 4, 2 times 2, and then the negative version. So minus 1 times minus 4 and minus 2 times minus 2. So our possible zeros, this is going to be great. We've got plus or minus 1, plus or minus 2, and plus or minus 4. So we need to find 4 zeros, and we've only got 6 possibilities. So nearly every single one we test is going to be a 0. It's just figuring out which ones are and which ones are not. So m over n. Now what that also could mean is that we have multiplicities in here. So that means that one of the factors is going to be repeated multiple times, in which case, even though there's 6 possible zeros, say 2 could be a 0 2 times, the factor could be x minus 2 times x minus 2. So we need to be aware of that it doesn't mean that every one is going to be a home run when we do it. Put in our polynomial 1, minus 2, minus 3, 4, and 4. Possible zeros, minus 1, positive 1, minus 2, positive 2, minus 4, positive 4. All right, so the 1 comes straight down. 1 times minus 1 is negative 1. Minus 2 is negative 3. Negative 3 times minus 1 is 0. Is positive 3. 3 minus 3 is 0. I'm getting ahead of myself in my head. 0 times minus 1 is 0, so we get 4. 4 times minus 1 is minus 4, so we get 0. Look at that. Once again, this minus 1, guys. It's a lucky one. Okay, so that would leave me with x cubed minus 3x squared. There's plus 0x, I'm going to keep it in there, and then plus 4. So now I need to go for another round of synthetic division. My factors are going to stay the exact same, or my possible zeros are going to stay the exact same. So I've got 1, minus 3, 0, and 4. I might as well test minus 1 again just to see. 1, minus 2, 2, minus 4. 1's come down every single time. 1 times minus 1 is negative 1. Minus 3 is negative 4. Negative 4 times minus 1 is positive 4. 0 plus 4 is 4. 4 times negative 1 is negative 4. 4 minus 4 is 0. Haha. So this is one of those ones where testing it a second time actually paid off, because it turns out that minus 1 is again another 0. So there's actually a multiplicity of 2 for x plus 1 as a factor. Let's look at that remaining quadratic. So we got x squared minus 4x plus 4 equals 0. Factors of 4 that add to be negative 4, that's this minus 2 and minus 2. So we'd have x minus 2 times x minus 2. Interesting, so another multiplicity of 2. So that means that all my factors together, I've got x plus 1, and then x minus 2, x minus 2. So they both had a multiplicity of 2. And my zeros, x equals minus 1, x equals positive 2. So if I were to kind of graph this, it would have been minus 1, positive 2. So it would have been this kind of turn up. So it's kind of like W shape where it turned on the axis both times. So just one that you wouldn't have guessed probably just from looking at the original polynomial. Now, one thing I do want to point out here is that you do have the ability to check your work on Desmos with this one. So if you plug the polynomial into Desmos, you will be able to see what the zeros are. Now, that is helpful in some cases. In today's lesson, it's a little bit more helpful because we're dealing with all real solutions. The next lesson, it won't be as helpful because you're going to have imaginary solutions as well. So I really do encourage you guys to check your work using Desmos, but don't use it as a substitution for the synthetic division. Like, actually practice the synthetic division because you will need it in the next lesson. So if I put it into Desmos, I would be able to see, okay, yep, there's zeros at minus 1 and 2, and it looks like this. So I can see that, I've got my multiplicity of 2 in both cases. And it's a great way to check your work. Like, I would never want you to not check your work, but just make sure you are still doing the work and not letting Desmos take over for you. All right, so how do I find the zeros of any given polynomial? We look at the factors of the constant and the factors of the lead coefficient. You do factors of the constant divided by factors of the lead coefficient. That gives you your possible zeros, and then you start testing them using synthetic division until you find ones that have remainders of 0. Once you do that, you can then move on to the quotient and either go through another round of synthetic division or factor it if you are down to a quadratic. In the next lesson, we'll see what happens if it doesn't factor. So like, we'll go into quadratic formula. We'll see that we'll have complex solutions as opposed to just kind of nice numbers each time. But hey, use it while you can. Make sure you check your work using Desmos. After today, complete the rational solutions of polynomials folder, and just make sure that you are finishing up that math task from last week, so the larger Khan Academy math task, and you're getting all of those completed.